Alexei, Leonid și Mihai. Îmi pare foarte bine. Leg. Trebuie să fiu mulțumesc. Da.
Dear Minister Nanotechnologies, Minister of Education and Research, dear Professor Viorel Bostan, Rector of the Technical University of Moldova, dear Professor Hiroshi Amano, Your Excellency, Ambassador of Japan, dear Vice Rector of the University of Medicine and Pharmacy, distinguished guests, dear colleagues, researchers, professors, students and friends of science, good morning. It is a profound honor and privilege to open today the 7th International Conference on Nanotechnologies and Biomedical Engineering, a major scientific event that brings together outstanding minds from around the world to share knowledge, inspiration and innovation. This conference is jointly organized by the Moldovan Society for Biomedical Engineering, the Technical University of Moldova and the Academy of Sciences of Moldova in partnership with the Nicolae Testimițanu State University of Medicine and Pharmacy, the International Federation for Medical and Biomedical Engineering and the European Alliance for Medical and Biological Engineering and Science. Held biennially, this conference was first inaugurated in July 2011, bringing together around 150 experts from 17 countries. Since then, it has evolved into a highly respected international forum known for the scientific quality of its proceedings, rigorously reviewed and published by Springer in a dedicated volume. This tradition of excellence has strengthened our international visibility and credibility in both nanotechnologies and biomedical engineering. Today, at the 7th edition, we are proud to welcome about 160 participants from 18 countries, from Europe, Asia, North America and beyond. Many of our guests have been long-standing collaborators and friends of Moldova, contributing to previous editions and helping to extend the global impact of our scientific community. It is also deeply symbolic that this conference takes place during the Nobel Prize Week, a time when the global scientific community celebrates the highest achievements of human intellect and creativity. Yesterday, the Royal Swedish Academy of Sciences announced the Nobel Prize in Physiology and Medicine, and in just a few hours, the new Nobel laureates in physics will be revealed. Against this inspiring backdrop, we are profoundly honored to have among us two Nobel laureates. Professor Hiroshi Amano from Nagoya University, Japan, Nobel laureate in Physics 2014, and Professor James Rodman from Yale University, United States of America, Nobel laureate in Physiology or Medicine 2013. He just landed, it's already here in Chisinau and will join us later. Their presence in Chisinau gives this event a historic and inspirational dimension. Professor Amano's work has illuminated the world through innovation and sustainability, while Professor Rodman's discoveries have deepened humanity's understanding of the molecular mechanism of life. Together, they remind us that science transcends borders, unites nations, and shapes the future. Dear colleagues and participants, nanotechnologies and biomedical engineering stand today at the heart of global progress. They bridge disciplines, physics and medicine, chemistry and biology, engineering and creativity to develop solutions that improve health, protect the environment and open new frontiers of sustainable development. Over the next few days, we will witness outstanding presentations fruitful discussions and new collaborations that will advance both science and society. I am confident that the results of this conference will further consolidate Moldova's image as an active and respected contributor to the international scientific community. On behalf of the organizers, allow me to express our deep appreciation to all participants, partners, and collaborators who have made this important event possible. I am pleased to convey my best wishes for success to all participants from the distinguished Professor Victor Șontea, whose enthusiasm was very important then, 14 years ago, when joining our efforts, we together managed to organize the first edition of the conference. Professor Șontea has dedicated a lot of time to organizing all editions of the scientific forum, including this one. But unfortunately, he is unable to be with us today due to health problems. Also, Ms. Alana Nimerenko, Minister of Health of the Republic of Moldova, who cannot attend our meeting, asked me to wish you, on her behalf, a successful conference with fruitful exchange of scientific ideas. I have now the great pleasure to declare the 7th International Conference on Nanotechnologies and Biomedical Engineering officially open. May this forum inspire us all to continue building bridges between disciplines, nations, and generations through science, innovation, and human creativity. Thank you. To give the floor to the host of this ceremony, opening event, Professor Viorel Bostan, Rector of the Technical University and member of the Academy of Sciences of Moldova. Please, you have the floor.
Thank you very much, Mr. President, Your Excellency, Mr. Ambassador, dear Minister of Education and Research, dear Professor Hiroshi Amano, dear colleagues, ladies and gentlemen, I'm very privileged to open this conference, because this conference is one of the important conferences organized by the Technical University of Moldova. And again, I would like to express my gratitude to one of the founding fathers of this conference, Professor Victor Șontea, who with his enthusiasm managed to gather here in Chișinău people from different disciplines, especially from nanotechnology, nanosciences and health sciences in this respected scientific forum. As the President of the Academy mentioned, nanotechnologies are basically a driving force, one of the driving forces of the current developments. People working at nanoscale trying to create new materials, to discover new properties, and based on that to have novel devices. And also, which is very important for us, is that this conference focuses not only on nanotechnology, but also on biomedical engineering, biomedical sciences, and it is exactly the case of a cross-border investigation, multi-discipline research, which actually today is probably one of the characteristics of modern science. We are very honored to be the co-organizers of this conference. I am very pleased to have here a lot of friends from previous editions and new friends from this incoming edition. This conference has very high scientific standards. That's why its works will be published in prestigious Springer Proceedings. And also I welcome students, PhD students, bachelor degree, master degree students, who probably today will be their first encounter with real science. Moldova has a good potential in nanotechnologies. We have several research groups well known across the border, and I'm very convinced that this conference will create new bridges, new collaborations. It will be a platform for discussions and for future projects. Thank you so much for your presence here, and I wish you a very successful conference.
Thank you, Mr. Rector. Now I am pleased to give the floor to the Minister of Education and Research of the Republic of Moldova, please.
Thank you. On behalf of the Minister of Education, I'd like to, first of all, congratulate you on organizing this extraordinary conference. It is an excellent opportunity for our researchers to get in touch with their international colleagues, also to have access to some of the most brilliant minds of our times. It is not something which is often happening in Moldova, so congratulations and great thanks to all the organizers that are making it possible. I'd also like to welcome Professor Hiroshima. It is a great honor to have you here, as is Professor Ottman, to have you here today and for you to be able to share your experience with our colleagues. And I'm very happy to see here very many students, which are the future of Moldovan science. And I hope your presence will also inspire them to aspire for excellence. On behalf of the Ministry, I'd like to say that we will continue supporting the organization of such events. It is part of our strategy for internationalization, and we would like to see more and more opportunities for cross-border collaboration. In recent years, we have been investing significant amounts of resources into this, and this will continue, and hopefully such kind of events will become a tradition across multiple fields in Moldova. In nanotechnologies, indeed, we have a long-standing tradition, a well-established research community, and I'm extremely happy and honored to be able to be here with you today. Our congratulations, and let this conference be a good opportunity for experience sharing and for new knowledge to emerge. Thank you so much.
Thank you. Now let me give the floor to His Excellency, Ambassador of Japan to the Republic of Moldova, Mr. Yaman. Please, you have the floor.
Thank you, Mr. President. Good morning. 部の皆さん、おはようございます。Well, thank you for this honor to be invited to this podium to say a few words. First, congratulations on having this very important event. And second, congratulations on Moldova choosing the clear path for development at the recent elections for the parliament. Because you are all scientists, I would like to say why I believe this is such a great event with a scientific probably explanation. Just 5 very, very brief points. One is the European integration, accession to the EU, which is sure to happen, which brings great benefits to all the new members of the European Union. Second, Ukrainian reconstruction, which is going to bring a lot of energy, excitement, money, and opportunities. And then with Moldova having an advantage, unique advantage to reap from this process and contribute to the benefit of the Ukrainians. 3, the brilliance of the Moldovan people, particularly the young people. We have seen in so many international competitions in the field of science and technology how well the Moldovan youth are doing, and every time I see, I'm not Moldovan, but I get really, really excited as ambassador that is posted to this country. 4, also about the people, your diaspora. It is true that for many years running, there have been a lot of exodus out of this country to work in the European Union and other countries. But this tide is going to turn. In the case of Romania, Poland, etc., the youngsters were unable to visit and live and try their luck in these countries until the countries joined the European Union. The Moldovan youth are already there. Their curiosity has been satisfied, and then they have accumulated enough skills, and then enough human network and enough money to invest back into this country. So they are now going to come back, now that the course of this country's future is bright and confirmed. And the 5th, the demographic composition. In the recent elections, we have seen that the age group 36 to 45 have a bulge. That's because you have had a baby boom in the 1980s. So they are now between 36 and 45. They are young enough to be energetic and then take a risk. And then old enough or mature enough to have established great human contacts and built up skills. So having this really enrich a group, a big group in the population structure to be waiting to participate in this country's great future revitalization. It is certainly going to bring a great stimulus to your country. So all in all, I'm convinced that the Republic of Moldova is going to see the highest economic growth in the world in the next 10 to 15 years. Probably we will be competing for that position with Ukraine after the end of the war. But I'm very, very sure that you have a very bright future ahead. And also it is going to stimulate your scientific community, academic development. And we only wish that Japan and Moldova will further develop our relationship. Lastly, very briefly, thank you for Japanese participants who came all the way. We had a nice little dinner last night, and then Professor Amano was telling us that when he nomination was the prize was awarded. When the award was announced, he was traveling en route from sorry, it may have been you who should have said it, but I said it anyway. En route from Japan to Germany and then to France. And then on his way there, he saw lots of congratulations, but he didn't understand what it was about, and thought that it was all spam mails. And then now one of the 3 laureates who received Nobel Prize for Physiology or Medicine yesterday, he's still not been contacted because he's walking alone in the mountains of Idaho. So that reminded me of that. But thank you, Professor Amano, for inventing this wonderful, LED device, thanks to which I no longer need to burn my fingers when I change the light bulb that has burnt out. So thank you very much.
Thank you, Excellency. Ladies and gentlemen, we organized this event in close collaboration, partnership with the University of Medicine and Pharmacy, Nicolae Testimițanu of the Republic of Moldova, the rector and Professor Emil Ceban cannot attend this morning event, but we have here the Vice Rector of the University of Medicine and Pharmacy, Professor. Please, you have the floor.
Thank you very much, dear colleagues, distinguished guests. It's very difficult to speak after this distinguished personality in Presidium. It's a great privilege to say these words of welcome for you on behalf of our rector, Emil Ciobanu, in the presence of Minister of Education and Research, the President of Academy of Science of Moldova, and distinguished Nobel laureates and Ambassador of Japan. This international gathering and conference uniting participants from more than 18 countries and demonstrate that science it's a universal language, building bridge across the borders and transforming ideas into solutions in the futures. The topics we address: biomedical engineering, nanotechnology, personalized medicine, and e-health, define tomorrow's healthcare and highlight the responsibility of science towards humanity. On behalf of Nicolae Testimițanu State University of Medicine and Pharmacy, I would like to extend sincere gratitude to the organizers, partners, and participants whose commitment makes this event possible. Let us remember, science is not only discovery. This is about building bridges of knowledge and hope for humanity's future. Thank you.
Thank you very much. Before we will have a 5 minutes break to prepare everything for the plenary session, I would like to ask Professor Hiroshi Amano, who arrived to Moldova to Chișinău yesterday. Direct flight from Japan to Frankfurt, and then from Frankfurt to Chișinău. Yeah, please.
Dear distinguished guests of the Republic of Moldova, His Excellency, the Ambassador of Japan, and ladies and gentlemen, it is my great honor to be here and give a presentation and discuss with the students. So I'm very, very happy to be here. So I'd like to thank the Professor Tignaniu and their organizers for giving me these opportunities. Yeah, this is my first time to visit Moldova. And I'm a bit surprised that this country is very nice. Fortunately, this is the Nobel Week, so I believe that the someone of Moldova's researchers will receive the Nobel Prize this time or in future. Anyway, thank you so much.
Yeah, yesterday we realized that Nagoya in Japan, the Republic of Moldova, have the same population, about 3 million of people. Therefore, Professor Hiroshi Amano said that there is a possibility that Moldova also become has a Nobel Prize laureate. Well, thank you so much, ladies and gentlemen. We will have a 5 minutes break, and we will prepare everything for the first plenary session. Thank you very much for your contribution. Back, now I would like to open the plenary session number 1. The first presentation will be delivered by Professor Hiroshi Amano. So the title of the presentation is "Why did a poor university spark the Blue Lead Revolution?" The title is very intriguing. So, Professor Amano, please, you have the floor.
Good morning. Thank you so much for the kind introduction. Good morning, everyone. I'm Hiroshi Amano, Naga University. So it is my great honor to be here and give a talk. So first of all, I'd like to thank the Professor again for giving me this opportunity. Yes. I presented online twice, but this is my first time to present in person. Today, I'd like to present how the blue LEDs and LED lightings have been developed at a very poor university in Japan. The poor university is our university, Nago University. And LED lightings, I believe that it contributes to energy savings around the world. It changes from consumer electronics to sustainable electronics. The reason is, compared with the incandescent lamp, LED lamps have 40 times longer lifetime and 6 times higher efficiency. So according to US Department of Energy, the people in the United States can save about 22.8 petawatt-hour over 18 years, which corresponds to 890 billion US dollars, which is huge. And this small chip has triggered a shift in the lighting industry from mass-produced, mass-consumed consumer electronics to long-lasting, recyclable, sustainable electronics. And the reason why this device emerged in Nagoya University is because of my supervisor, Professor Asaki's strong commitment to his original LEDs, or other words, he thought he should not bow down to the United States. Let me explain the reason why. When he was in the junior high school student, it's the age of the World War II. And he was born in Jilan, famous for an Army Special Attack Unit base during World War II. Army Special Attack Unit base means all the pilots were kamikaze suicide attacks. And so the attack from the United States ships are very, very strong. And when he was going back to home from the junior high school, he had experienced machine gun irradiation from a Grumman pilot, and he saw a pilot sneaking. Okay. Then he entered the Kyoto University in 1952, and then graduated the School of Science, majoring in chemistry. So material. And then he entered the Kobe Kogyo. Now the Kobe Kogyo was gone, but it's like a Sony today. And then he developed fluorescent material for full color displays. Because in Japan in 1953, the TV broadcasting, full color TV broadcasting started. So he concentrated on developing fluorescent materials. And then he moved to Nagoya University, where he developed germanium crystal growth. And then, after getting the PhD, he moved to Panasonic, where he encountered with LEDs in 1964. The business was so successful, the red and green LEDs manufacturing so successfully, so he received the President Award. However, he had to follow the patents owned by the US companies. So he was pursuing his originality. That's why he started researching blue LEDs. The material is gallium nitride, compound of gallium and nitrogen. And the first success was done by RCA Group, the United States. Dr. Maruska and Dr. Tijan succeeded the single crystalline gallium nitride growth by halide vapor phase epitaxy in 1969. And then 2 years later, Dr. Jack Pankov succeeded the MIS type, metal insulator semiconductor type blue LEDs based on gallium nitride. But it's not the PN junction type, so the efficiency was very, very low. But following their success, many famous electronics companies all over the world tried to follow his achievement, like RCA, Oki, Hitachi, or Philips. However, it had been very, very difficult to grow even the single crystalline gallium nitride at that time. So almost all the companies abandoned the blue LED. But Dr. Akasaki insisted on continuing the research on gallium nitride blue LEDs, and he started, by the support of Ministry of International Trade and Industry pilot project, he started the gallium nitride growth by molecular beam epitaxy. At that time, MB technology was still in its preliminary stage. So many people said you should not do it. But overcoming fierce opposition from those around him, Dr. Akasaki decided to start growing gallium nitride by molecular beam epitaxy method. So result was disaster. Akasaki's team could not succeed in fabricating the blue LEDs by MB, so he had to switch the growth method to halide vapor phase epitaxy and succeeded the MIS type LEDs. However, he had to use the patent owned by the US companies. So if a company decide to commercialize, the Matsushita or Panasonic had to pay a lot of loyalty to the US companies. Therefore, the manager of Matsushita decided to cancel the blue LED project and suggested him to start long wavelength or other research subject. Therefore, he gave up on the company and moved to Nagoya University in 1981. At that time, almost all the industry players around the world had abandoned gallium nitride-based blue LEDs and started working on zinc selenide, other material blue LEDs. So he said, I walked along in the wilderness. Why it had been so difficult to grow single crystalline gallium nitride? If the people want to grow bulk growth gallium nitride, they need very high pressure, 45,000 atoms, and high temperature over 1500 centigrade. So we have to use the falling materials as the substrate, and the sapphire was used. But there is a very large lattice mismatch, over 60%. So the gallium nitride crystals grown by HBP by early 1980, there are a lot of macroscopic defects such as cracks, pits, and voids, prohibited the realization of beta gallium nitride and the manufacturing commercial royalties. Then he moved from private company to National University, Nagoya. But at that time, the university in Japan was very, very poor. This is the funding, research funding each year. So it's about 20,000 US dollars per year. But he insisted on doing his original growth method. So he tried to use the metal organic vapor phase epitaxy method. In the mid-1980s, Japan was close to a bubble period. So the companies had a lot of money. However, they spent lots of money for American universities, not for Japanese universities. So the requirements for today's efficient royalty, there are 3 requirements. Okay. And at that time, no one succeeded to grow high quality gallium nitride crystals. So we have to start how to grow the high quality gallium nitride crystals. Unfortunately, we are fortunate enough to obtain spare parts and raw materials through Professor Akasaki's connections. For example, the company provided chromate because they are rich. The company provided flange, and for heating, we made handmade coil using a beer bottle. After heating the copper tube and heat by burner and winding it to the beer bottle, we can get the very beautiful heating coils. So in such a way, we started the crystal growth. This is me. And the gas is the hydrogen, and the temperature is 1000 centigrade. So it was very, very dangerous. However, at that time, no one was concerned about the safety issues. So I can start such an experiment. And to tell the truth, we are the latecomer for the growth of gallium nitride by metal organic vapor phase epitaxy. In 1971, Dr. Manasevich team, North American Rockwell, succeeded the epitaxial growth of gallium nitride on the sapphire substrate. So I concentrated on growing gallium nitride for 3 years. Bachelor's, master's, first master, and second master's. I have almost tried almost every day for 3 years. 364 days per year. But I could not grow high quality gallium nitride films. At that time, I thought I have to supply source gases with a very low speed. But I couldn't succeed. So I went to the Tokyo University, and Professor Tsubouchi and Dr. Masu conducted the aluminum nitride growth by MOVPE, which is like a brother materials. And I was so surprised that they use the low pressure growth system and very high speed gas flow. So I found my mistake. We have to use a high speed gas flow. But we did not have a good pressure control system, and the capacity of the gas purifier was very, very small because we are very poor. So I decided to use the atmospheric pressure growth system and the high-speed gas flow with one very tiny nozzle, 6 millimeter in diameter, and then we could grow the better gallium nitride, but not sufficient. But at the end of master's course, I finally succeeded to grow high-quality crystals. The first, I plan to grow thin aluminum nitride. Aluminum nitride research has been done by Mr. Koide, who was 1 year my senior. And Koide's aluminum nitride are flatter surface than my gallium nitride. And I know that to grow aluminum nitride, we need a higher temperature, 1200 centigrade. But I found that the growth furnace was in a bad shape and could not reach the temperature required for aluminum nitride. But I was in a hurry. I have to get the PhD. So I tried to succeed the experiment. And when the growth was finished and the vapor was taken out of the growth furnace, the surface was the cleanest I had ever seen. So I thought, oops, I forgot to pour out the raw material. I checked to make sure I did not have made a mistake. I looked at it under the microscope and found that the perfectly flat gallium nitride had grown. I was moved beyond words. So, I was happy to write a draft of the patent and general paper to get a Doctor of Engineering. Okay. And it was soon accepted for publication. However, my paper did not catch the attention of other researchers because there were no gallium nitride researchers at that time, I suspect. There was zinc selenide booming all over the world. But in such a situation, Japan Science and Technology Agency outsourced the gallium nitride blue light emitting diode manufacturing technology to Nagoya University and the Boses. Before 1987, total budget of our laboratory was 3 million Japanese yen. It corresponds to $20,000 per year. But after that, the situation changed. It's $3.8 million. And since the Boses succeeded, the license fee was 4.6 billion Japanese yen. It was huge. Let me explain the reason why the JST invested to gallium nitride. Blue LEDs was required and JST definitely wanted to realize it, and JST recognized that blue LEDs is a very difficult issue. Therefore, it is necessary to go back to the basics and tackle from the material development. And many researchers are working at universities and research institutes, and steady research is required. So JST staffs visited major laboratories in Japan in sequence, but most of them were basic research, such as luminescence property research, the so-called academic research. So it was extremely difficult to find a research result that could lead to the practical application of blue LEDs. It should be impossible to realize during the 20th centuries. So high-priced equipment was required for semiconductor research, and there was insufficient funding to create technological seeds that could be put to practical use at the university at that time. So in such a desperate situation, why JST budgeted for gallium nitride blue LEDs? JST staff visited Professor Akasaki November 1985, he was very, very surprised at the success of producing a high-quality gallium nitride crystal. He definitely wanted to pick it up to industry-academia collaboration project. So the Nagoya University needs industry partners. Then he proposed patent application to Professor Kawasaki, so I wrote a draft. And in November 1985, Professor Kawasaki presented at the Nagoya Chamber of Commerce and Industry lecture to the Gosei. People paid attention to it. On December 20th, Professor Kawasaki called JST that the Gosei people are interested in this development. So, 1986, the Gosei visited JST, and 1987, development officially started. However, at JST, there had been a very strong opposition. Blue LED was a heavy load for JST. The favorite was zinc selenide, another material. Okay. Could Toyota Gosei really carry them? Toyota Gosei was a lava company, no experience of semiconductor device development. So, but only one person said, there was no prospect of success even with zinc selenide. If so, why not to try gallium nitride? So I could say that research needs gamblers. Anyway, but in my case, I had to publish 3 journal papers in my PhD program in order to get my Doctor of Engineering. So this is why I began my challenge to realize P-type gallium nitride. And it was a very stressful experience. This is the gallium nitride crystal model, and this is gallium, and the green one is nitrogen. To get the P-type gallium nitride, we need to replace gallium to column 2 element. Like at that time, we used the zinc. So zinc has 2 valence electrons. The gallium has 3, so 1 electron is missing. Therefore, the zinc captures 1 electron from the valence band and it becomes false. That's the origin of P-type conduction. However, many people said that the gallium nitride is ionic in nature, so it becomes very, very unstable. Therefore, the neighboring nitrogen is missing, which form the nitrogen vacancy, and nitrogen vacancy provides electrons to the conduction band, and this electron compensate this pole. So many people believe that this compensation effect prohibit the realization of P-type gallium nitride. However, I was very young. Okay. I believed that I could realize P-type gallium nitride even though there was no evidence at all. I experimented a lot, but I still could not do it. So, 3 years of the doctoral course is a series of stressful experience. The mood in the lab at that time was I should make a blue LED with conventional MIS type, not the PN junction type, and write a paper on it, and then go on. But the lighter material, zinc selenide, there had been a series of P-type reports, and MIS type LED by MOBP had already been made. So the old MIS type blue LEDs already done by others did not motivate me to write a paper at all. So my stress was maxed out. So my experience gained here is follow the belief that I have grasped for myself, or in other words, better not to follow all people's advice. Okay. Let me explain the reason why. that I am the one doing the most experiments in the world right now. Later I realized my mistake. There are much more amazing people in the US and Europe. But I had a feeling that in the near future I will have a P-type gallium nitride. But this is a totally unfounded confidence. However, in my doctoral course, I did many experiments but could not make P-type gallium nitride. I thought there must be something that I do not understand yet. So I learned the courage, the persistence not to do something until I found the path to my goal. Then, as a result, I was not able to complete my Doctor of Engineering and have to leave the doctoral course. However, thanks to Professor Kasaki, I was able to become a research associate even without a PhD. Okay? Therefore, I was able to continue my challenge to realize P-type gallium nitride. And immediately after I became a research associate, I was very excited to see the path to my goal. In case of gallium phosphide, the magnesium should be better than zinc in terms of the P-type conduction. So, my mistake was the element. It's not zinc, but magnesium. So finding the goal of being the first in the world released all my stresses. And the aggressive growth was done by Mr. Akito. He was the master course student at that time, and he grew magnesium-doped gallium nitride, but at that time it was compensated. So we need a treatment, electron beam irradiation treatment, 7 hours. So, Naga University people do not want to do some long treatment. So, I went to the Gosei to rent the electron beam systems. So, 1 hour by small scooter and 7 hours for treatment, and then return to Naga University. It took me 9 hours to make one sample, but at that time I was desperate to get my Doctor of Engineering, so 9 hours was nothing to me. And then finally we realized P-type gallium nitride and PN junction LEDs. Origin of passivation of magnesium had been clarified by Dr. and Dr. Van Bechten. It's a hydrogen passivation. So, two barriers have been already solved. So, only one remaining barrier was indium gallium nitride. We started the indium gallium nitride research maybe the first time in the world, but soon gave up. In 1987, so the elder researchers, in this case, said indium nitride and gallium nitride should be immiscible materials. So the reason why we could not grow indium gallium nitride is because of the immiscibility. However, 2 years later, Dr. Matsuoka at that time, NTT, now the Tokyo University, he and his group succeeded the growth of indium gallium nitride. Why we could not grow and he can grow is only the difference of the carrier gas. He used nitrogen as the carrier gas, while we used the hydrogen as a carrier gas. The difference is only the difference of carrier gas. Unfortunately, however, his indium gallium nitride did not emit light at room temperature. The group which succeeds, the highly luminescent indium gallium nitride and succeed to fabricate the blue LED was the Nichia, read by Professor Nakamura and Dr. Mukai. And many people say, why only the blue LED received the Nobel Prize? There are other colors of LEDs. One of the reasons this is the blue LEDs, and only the blue LEDs can realize the white LEDs with the combination of phosphors. The other colors cannot realize white LEDs. So we can use this combination for LED lightings. Okay, this is our blue LED development stories. And this material system can be applied not only the optoelectronics but also the power electronics. This is the three-dimensional earth globe displays developed by Professor Takemura, Kyoto University of the Arts. And this is Africa and this is Europe. You are here. And in winter, this red shows the highly CO2 contaminated air. Okay. In the winter, European people emit a lot of CO2. However, in summer, it disappears. The reason is Siberian forests are absorbing CO2 from the Europe. Okay? So I can say it's a collaboration with Europe and Russia. However, CO2 emission gradually increase. Okay? So we have to suppress the CO2 emission. That's why we are trying to develop new semiconductor power devices for much efficient systems. The power semiconductors is like a heart of the human. The silicon is like a brain, memorized on the calculation. But the power device provides the sufficient power to all the systems. So it's like the heart of the human. And compared with the conventional silicon, this is breakdown voltage, and on resistance means like a loss during operation. So by using the silicon carbide or gallium nitride, we can reduce the loss almost 2 orders of magnitude. Okay? Because of the high breakdown electric field. And even compared with silicon carbide, the gallium nitride have much higher channel mobility. Therefore, we can switch with very high speed. So we can reduce the total systems. And this is strong and recyclable material, so it's sustainable. Let me explain why we need an efficient power conversion system. If you want to operate your PC at home using the solar panels, solar panel provides the DC power, but at home you use the AC power. So you have to convert from DC to AC, and then again AC to DC and control the DC voltage. So in average, you use 4 times the power conversion. And each conversion, you have 90 to 95% efficiency. So in average, 93%, which is not so bad. But if you convert 4 times, the total efficiency is reduced to 75%. So about a quarter of electricity generated generated by solar panel is lost. So that's why we need much higher conversion efficiency system. So that's why we're now concentrating on developing a silicon carbide and gallium nitride devices. And we apply this material for electric vehicle inverter. In electric vehicle, the lithium-ion battery is used. It's a DC, but motor is alternating current, AC motor is used because of the high efficiency. And we realized the 65% reduction of inverter loss in electric vehicles. This is our electric vehicles. We call it all GAN vehicles. The charge is the Mercedes because the testing is very difficult. We cannot drive outside our campus. So this is our inverter system. And then we operate the electric vehicle only by the gallium nitride inverter. Maybe this is the first time. So I hope that the young researchers in Moldova, now it's your turn, so please do not waste your gift of time. Thank you so much for your kind attention.
Thank you for the very interesting and wonderful presentation. And so the paper is open for discussion. Question, Professor Fomin, Vladimir Fomin, please. Please take one of these.
First of all, thank you very much for your extremely motivated and motivating talk.
Thank you.
One of your statements was about for some period the universities were poor. I like to tell now from my personal experience that your universities and in general Japanese science was extremely rich with bright mind, with discipline, with enthusiasm. I can recall only Professor Noboru Kimura, who was a front man of high-magnetic fields remains. And Yasuhiko Arakawa, who was one of the partners of London dots. And your work, which gave us beautiful instruments for sustainable development of all kinds of technologies. Now my question, you give beautiful explanation a little bit towards modern problem. You explained, it was very fascinating how you arrived at the idea of magnesium. It was not so easy and sometimes even internal meditation. Do you think that this way which you did as an excellent example of natural intelligence could be done now with artificial intelligence? Thank you.
Okay, very good question.
By the artificial intelligence aid, is it possible to expect the magnesium usage? Okay. Yeah, that's a very important question. Yeah, my answer is I'm not sure. But yeah, now it is possible to expect by the artificial intelligence to use magnesium, but at that time, the several groups also uses the magnesium, but they
For example, the RCA and the OK electric use the magnesium, not the zinc, but they couldn't realize the B-type gallium nitride. So at that time, maybe even the good AI exists, it may be difficult to expect the magnesium to be the candidate for B-type gallium nitride.
Yeah, thank you. Thank you. Other questions, please? So, no other questions. I think that there will be a coffee break and the discussions will be continued. But we once again congratulate you with your big contribution to the development of lighting technologies. You really succeeded in making a breakthrough in that time. At that time. And thank you for your visit. We are very happy that we are together. It's raining, unfortunately, but raining is good for the success of the conference.
Great pleasure to share the second part of this opening lectures. I think I don't have to introduce Ian Tegenyanu. He's very well known, and now he gives continuation on gallium nitride. So he will present the research on gallium nitride in the Republic of Moldova. Please, the floor is yours.
So actually, that we started to deal with gallium nitride about 24-25 years ago. After I realized the project at the University of Michigan in the United States, I came home with two ideas. One was to create a center of material science at the Technical University, and the second one to start serious research on gallium nitride. And actually, we were influenced by the papers of Professor Hiroshi Amano, because at that time he succeeded already to demonstrate the light-emitting diodes on gallium nitride. And on the other hand, people became interested at the intersection of two centuries in gallium nitride, because gallium nitride is a material of choice for higher frequency and higher power electronics. That means the first success, breakthrough, was lighting technologies, and Professor Hiroshi Amano was, let's say, one of leaders at that time with his colleagues. And the second one, higher frequency, higher power electronics. Nowadays, we already approached the third, let's say, dimension of use of gallium nitride is biomedicine. And here, again, very interesting issues. So you see the outline, very importance of gallium nitride, and I will tell about what we succeeded to develop, to realize here in the Republic of Moldova, and with the time, of course, in close collaboration with the research groups from other countries. And Professor Rainer Radelung is one of our partners. We succeeded to develop interesting things I will tell you later. Why gallium nitride? We started 24 years ago to study this material. It's a material with direct and wide bandgap, good for lighting technologies, and Professor Hiroshi Amano already told about this. He possesses high chemical stability, stable at higher temperatures. Good for lighting technologies, blue light emitters. We already had one report, and as I mentioned, it's good, very good for high frequency and high power micro nanoelectronics. And nowadays is very interesting for use in biomedicine due to the fact that it's a biocompatible material. You see the advantages of gallium nitride versus silicon. Well, I will not stop, but it's clear, especially you will see here, gallium nitride is actually very good for the point of view of higher frequency and higher power. You see indium phosphide, for instance, very good for higher frequency applications, but not good for higher power applications. And it's very interesting that if we speak about solid solutions between gallium nitride with indium phosphide and aluminum, indium nitride and aluminum nitride, you see that these solid solutions may cover a very broad spectrum. It's a unique material system, actually. And well, gallium nitride has rapidly transformed the world by enabling energy-efficient light-emitting diodes and promising energy-efficient power electronic devices. And realized that between gallium nitride and zinc oxide, the mismatch is very small, negligible mismatch. And you see gallium nitride and zinc oxide possess nearly the same band gap, and well, the difference in exciton binding energy, and this actually also gives interesting features. But for us it was very important that that mismatch is negligible. And well, I remember many years ago at a conference in Grenoble, at a SPIRE conference, we were organizers of that conference. And we decided to try to deposit gallium nitride on zinc oxide, and the interesting issue is that the mismatch remains negligible even if you change the temperature. Because you see here to the right, well, we have here very close thermal expansion coefficients. And so, taking this into account, about 20 years ago, we developed a new technology. We call this surface charge lithography. I will tell you what is the meaning of this approach. The idea was actually very simple. So to write negative charge on the surface of the gallium nitride and to use photoelectrochemical etching, and the expectation was that negative charge will shield the material against photoelectrochemical etching. That's by definition, because what it means to remove an atom? To cut the chemical bonds, to remove electrons. But when you have negative charge in excess, obviously you will fail to introduce a hole and to remove an electron. So for this technology, we got an award of excellence at an international exhibition of new technologies and new products in Pittsburgh, United States of America. You see actually here you see the idea. You can write negative charge by various means, and with subsequent photoelectrochemical etching you will get structures. Of course, the first experiments were very, how to say, exotic. For instance, by using a wood needle just to write some lines. And we introduced negative charge in the defects that we introduced by the needle, wood needle were negatively charged. And this survived during photoelectrochemical etching. We're using a diamond microscribe, as you see here. And during photoelectrochemical etching, we observed that these areas are not etched. At that time we succeeded just to write Moldova by using this technology that will be introduced here by irradiating with ions, and the generation of negatively charged effects, and photoelectrochemical etching led to the appearance of these letters. So actually, as I told, the idea was very simple, and by using this approach, we succeeded to develop different structures, nanomers of gallium nitride on the top, or nanomembranes, simple nanomembranes as you see here. But the most important, we came to the conclusion that, in fact, using this approach, we can fabricate membranes, and this was a breakthrough in our approach. The idea was to irradiate with ions at low energy and low dose, to introduce defects enough that so the material is shielded against photoelectrochemical etching, but to allow ultraviolet light to go through, to etch underneath the membrane that emerges. And we observed that we actually get these membranes, but we have here a lot of wires. And the wires actually represent threading dislocations. Fortunately, they are negatively charged. Therefore, we succeeded to prepare, I will show you such membranes, you see such membranes here, but underneath a lot of wires of gallium nitride that represent negatively charged dislocations. And you see with the time, we actually came to the conclusion that it's possible to remove these dislocations because there is a threshold. In case you are very insistent, you can optimize the conditions to remove the dislocations. But it was necessary to have columns, nano columns, micro columns for the physical support. And we came to the conclusion that we can just use higher dose of irradiation where we would like to have such a column, because in this case the material here will not be transparent to the ultraviolet light, and during the photoelectrochemical etching you will form a column. And of course, low dose of irradiation means that it will be transparent, and only the top very thin layer will survive. And as a result, you will get membranes, as you see here. That means membrane that has for the physical support different kinds of nanoballs, microballs, and so on. But all these have been, let's say, designed and fabricated, controlling totally the situation. So these results have been highlighted on the cover of and also there was a nanotech report in London that highlighted this success. And it's a very, I think that was a real success that we succeeded in developing photonic crystals. Ultra-thin photonic crystals. That means you see here photonic crystals that to fabricate these photonic crystals, we actually have not used the classical, let's say, nanotechnological approaches. Just direct writing by focused ion beam and photoelectrochemical etching. That's all. You see our ring resonator there, you see the gas splitter here, you see some defects in the photonic crystals here, for instance. Yeah, and here, waveguide in the photonic crystal. to see what happens, you look here. So underneath everything is removed. That means we have a very thin membrane. It's actually 15 nanometers thick, and it's actually possible to have this membrane and to transfer to the substrate. But of course, this needs a very careful approach. So this was developed in the first decade of this century, and we succeeded after that to publish this. And actually, there were a number of papers in applied physics letters starting from 2005. And here you see the nanoperforated gallium nitride membrane. You see that the membrane, you have metallic contacts on both sides, and what we have demonstrated here, that we have a very pronounced conductivity, persistent conductivity, and it's possible to control this persistent photoconductivity by additional light with different wavelengths. An interesting issue actually was that we demonstrated that a network of dislocations in a solid state material can be visualized. And the idea was very simple. So you see these dislocations. They are fixed by the membrane on the top, and between the membrane and here we had the sapphire substrate, and actually this was the paper was membrane-assisted revelation of the special nanoarchitecture of dislocation network. And also was highlighted by literature. Now, I would like also to note that we developed memoristic devices based on gallium nitride nanomembranes fabricated by surface charge lithography and demonstrated their habituation to stimulus. And well, I will show you actually the behavior. Resistor with memory, but a very important issue is that a single gallium nitride membrane can support currents as high as 60 milliamperes, as you see here, at 9 volts, and a power more than a couple of watts, without any signs of failure. That was a real success to demonstrate that these membranes of 10-15 nanometers thick, they can serve as components for devices. So memoristic habituation to a stimulus, what we demonstrated, that the habituation depends upon the number of memristors. That means the number of these membranes. If you have a single memristor, or just one membrane, then the habituation will be slow, as you can see, for instance, here. But if you have a network of memristors, the habituation is relatively fast. That means you come to steady state. And the last issue related to these membranes. We realized that in some cases, these membranes, due to internal stress, they just roll up. And you see, we get microtubes, by the way, with the gradient of the diameter. And in this case, in case you illuminate with the light and induce chemical reaction inside, of course, the products will usually gas bubbles are created, and they are ejected by the large diameter end. And you get engine, and you will see such an engine here. Under irradiation, it will move. In case you stop the irradiation, it will stop. Well, this was actually our first attempts to demonstrate the possibility to create light-driven engines. With the time, we developed more sophisticated. Here you see already an engine, a micro-engine that was developed using as the starting component zinc oxide column. We deposited gold dots on this column. After that, we deposited gallium nitride. As a result, we got, you see there, we got gallium nitride microtubes with a lot of nanowires inside, ended by metal dots. And these architectures are very good for use in photocatalysis. And you will see now a micro motor based on gallium nitride, one small micromotor, another bigger one. So this research was done in very close collaboration with our colleagues from Kiel University. Professor Rainer Arjun is here. We also worked together with Professor Lawrence Kinde in Kiel. Now I will pass to another very interesting subject, and I already made reference that many years ago, probably this was in 2013 in Grenoble, we discussed the idea to use the very negligible mismatch. At that time this was an idea, but it worked perfectly. And so we succeeded to develop the first artificial material with dual hydrophobic properties. So the technological approach is relatively simple. In this case, we used the micro-tetrapods of zinc oxide deposited by hydroxide gallium nitride. During the process, zinc oxide, the template, the sacrificial template is removed, and we came to hollow gallium nitride tetrapods, micro-tetrapods. That means we start with zinc oxide tetrapods and we come to a situation where we get hollow gallium nitride micro-tetrapods. But we should remember that on the inner side of these hollow tetrapods, we have an ultra-thin layer of zinc oxide. Practically, it's not possible to remove a few layers of zinc oxide from inside. And that's another very, very interesting issue. We realized that actually these tetrapods are very interesting because the lateral walls of arms are hydrophobic, while the free ends of arms are hydrophilic. Why? Because here we have polar crystallographic planes. A polar plane is charged electrically. A charged plane will attract water molecules because water molecules are dipoles and they are attracted by charged planes. That means here we have hydrophilicity, there we have hydrophobicity. And you see this material here, irogalnite, we called it irogalnite. It's a piece of irogalnite consisting of these hollow micro-tetrapods. It floats on the water surface. Here you have a droplet of water. It shows that it's hydrophobic, but in fact it's both hydrophilic and hydrophobic. And the density, specific density is very low, obviously, because we have microtetrapods, hollow, empty inside. And the thickness of the walls is just 10-15 nanometers. That means it's more air than material. The degree of porosity of this material reaches 98-99%. So obviously you see here the interaction with the light, and obviously we have here a spread of dimensions because the thickness of the wall is in the nanometer scale, but the dimension of the tetrapods in the micrometer and so on, and therefore scattering of the light is very strong. And physics world, after we published the paper in nanoenergy, highlighted this result, and you see here on the top, it's a demonstration that the material is hydrophobic. Here is a demonstration that the material is hydrophilic, because when you attempt to take the material from the water surface, the water doesn't allow you to do this. Formation of the column of water. Here, so it's schematically shown that the material is both hydrophobic and hydrophilic. Here you have a column of water. It forms when you try to take the material out from the surface of the water. And here some demonstrations. Formation of the column of the water. When you attract the material, here is a charged column, and the charged column attract the material, but you see the water doesn't allow you to pick it up. And here you see in real time, and here 15 times slow, you see the formation of the column of water when you try to take the material out of the water. Here we demonstrated that it's possible to remove plastic component from this material and to get a very elastic material. And so here you will see how this material behaves. Here is a charged stick, and in a non-uniform electric field you see the behavior of this material. Inspiration from nature. Well, that was really very interesting and inspiring, I would like to say. And we observed that these hollow gallium nitride microtetrapods interact with each other. There is attraction. We observed this when they were on the water of the surface, and we found that a similar interaction between fire ants. And I will show you. So fire ants interact on the water of the surface for the purpose of survival. During floods, one fire ant cannot swim and therefore dies. But they interact and create such floating raft, and the same actually happens with our, people call them artificial insects. And I will show you some pictures. You see here how the interaction, these are real pictures between fire ants and between our hollow microtetrapods. You see fire ant on the surface of the water, and how they succeed interacting on the surface of water to survive. Here it's a real picture, a real movie, and you see the interaction. You see that during the floods they succeed to reach the show, and you see that the ions interacting, they succeed in surviving. And I will show you the interaction between individual tetrapods. You see here one single tetrapod on the surface of the water and some fragments. And you will see that it is attracted and it's finally trapped by the fragment. And step by step you may create such rafts consisting of gallium nitride microtetrapods. Here you will see again the attraction of a large fragment. And you see here one single microtetrapod on the water surface. You see a network of microtetrapods on the water surface. You see here a raft of iron garnet. And you can actually put a droplet of water, and so the raft will float. It's a floating raft, and it may carry this droplet. Of course, in case you put too much water, then the raft cannot carry it. Here will appear a hole. Some colored liquid will go out, and after that the hole disappears and the raft is floating further. That means so these rafts can self-healing possibilities for these rafts. Here schematically you see the interaction between gallium nitride tetrapods. It's very interesting that there is interpenetration between these tetrapods. That means on the water surface, we observed interpenetration. And of course, we can control the degree of interpenetration. And you will see here, that we have here communicating vessels that in another arm we just add and remove water. And you see the surface increases, decreases. You also see here, and you have also a droplet of colored liquid on the top. That means it's stretchable, and stretchable due to the fact that we can change the interpenetration of this whole tetrapod. You will see here a more convincing example. Again, here we have communicating vessels. In another arm, we add and remove water. That means this membrane is stretchable and actually possesses very interesting properties. Now I will tell you about liquid marble. What is a liquid marble? A liquid marble is a droplet of liquid covered by nanoparticles, microparticles, as you see here as an example. And we created liquid marbles using hollow gallium nitride ionotetrapods. You see a floating liquid marble. You see in cross-section schematic, of course, just to realize what is this. And now you see the formation of liquid marbles. That means in case you have a bed of these microtetrapods, so the hollow microtetrapods will skim on the surface, and due to attraction will form this shed, like you see here, shed of tetrapods that actually covers the whole surface of the droplet. That means the liquid droplet is embedded in this shed of microtetrapods. And the interesting issue is that the liquid marble created in this way, it exhibits very would like to say properties. For instance, we took such a liquid marble, allowed it some time, and some liquid evaporated, and the interpenetration of tetrapods increased. And such a liquid marble is very stable mechanically. For instance, you put a liquid marble in between two pieces of glass, and and you see deformation is very strong, but it survives. It's just a droplet that is covered by this hollow tetrapods, and it survives in ultrasonic field. You see here treatment with intense ultrasonic, and you see that the liquid marble survives. And examples of self-propelled liquid marbles. Self-propelled, it means that we add to the liquid some volatile compounds. The compounds evaporate in all directions, but the speed of evaporation is a little bit different. And as a result, the gradient of the surface tension appears. And you will see here the movement of this liquid marble on the surface of the water, and actually in the field of surface tension gradient. And we succeeded to change the form, modify the shape, and to reach the prepared liquid marble showing a very fast rotation, as you can see here. Of course, if we analyze the speed of the rectilinear movement or rotation with time, it goes down because the concentration of the fuel goes down, of the volatile compounds. So you see here that the speed of rotation, for instance, reaches 750 rotations per minute. Here is per second, just for, yeah. And the question was how actually it's possible to reach very high speeds of rectilinear movement, of rotation. And here nature assisted us. So we found that there are insects flying water lily beetle that show they are skiing on the water surface. And the interesting issue is that so here we have the legs, they are hydrophobic, while so here we have hydrophilic, the claws are hydrophilic, the claws are tethered to the water surface. And you will see how they are skiing on the water surface. So you see the wings, the role of the wings in our case plays the surface tension gradient. That means in the surface tension gradient our liquid marble. But here the insect is skiing on the water surface because the claws are tethered to the water. And the same in our case. So the ends or the ends of arms of tetrapods are tethered to the water surface. Therefore, we have skiing. And I will show you just pendulum-like movement. You see the geometry, the liquid marble is here, the space between liquid and glass, and so it rotates. When it rotates 180 degrees, the sign of the gradient of the surface tension change, and therefore it rotates in such a, it shows a pendulum-like oscillation. But what actually we found that it's not a single rotation in on the surface of the glass, because it rotates really on the surface of the glass. But the free ends of some arms actually touch the water. And of course it's an attempt to detach these arms from the water. And this makes the rotation very complicated, and it's possible to have such pendulum-like oscillation as I showed. In case you succeed to detach the liquid marble from the glass, then it will skim, like we expected. In this case, it will skim on the water cells. Yeah, he's skiing. Okay, examples of applications. I should probably, I have 5 minutes probably. Two. So, examples of applications. Shielding, we demonstrated electromagnetic shielding in both gigahertz and terahertz. In this case, actually, the material behaves like a metamaterial. That means it's an interesting situation because the aerogamite is consists of hollow tetrapods. It exhibits relatively high electrical conductivity. That's very important. And we demonstrated shielding in gigahertz, also in terahertz, and for instance, shielding effectiveness in aerogamite exceeds 40 decibels in terahertz region, being among the best terahertz shields known today. So it can be used industrially actually. Pressure sensor up to 40 atmospheres. So here you have photocatalytic degradation of tetracycline by aerogamite. Also, it's promising for photocatalysis, this material. And well, the last issue, I would like just to mention that we developed also hollow nanoparticles for biomedical applications. What we observed that these nanoparticles are attracted by the living cells. As you can see here, you see here that living cells attract these nanoparticles. At the end of the story, we found these nanoparticles inside the living cells. You see the behavior of living cells without and with nanoparticles. So the nanoparticles do not actually affect the proliferation activity of living cells, in this case endothelial cells. And we found at the end of the story these nanoparticles inside the cells in vesicles. They found them in vesicles. That means you see here nanoparticle and just attracted. After that, the membrane starts to develop in such a way that it also grows around the nanoparticle and form a vesicle, and it will appear in the cell in a vesicle. Since this was gallium nitride doped by iron, that means it possesses magnetic properties, we used a magnetic field just to guide these cells. And you see here distribution of the cells, top uniform without particles, and distribution in the magnetic field when you have this kind of nanoparticles with magnetic properties. Just to show you that during these years, when after we created the center, many people, young people, did research, succeeded in defending their thesis. We have already one person, Fedor Monaco, defended the second thesis, Tudor Braniște is now preparing the doctor habilitate thesis. There are people that continue their activity at the center. And so summer schools in 2023, you see here that Hiroshi Amano opened the summer school. At that time, we had many prominent professors from different countries. This in 2024, the summer school. This is the summer school in 2025, opened by Professor James Rockman, and he landed 1 year, 1 hour ago to the Chisinau airport and will join us. And the most active was Professor Hiroshi Amano. You see how many times he contributed to different events at the Academy of Sciences of Moldova, and he was elected honorary member of the Academy of Sciences of Moldova, and we congratulate him with this. Thank you very much for your kind attention.
Thank you very much, Professor Tignano. Are there questions to this presentation? So we had a big journey in this whole session from basic physics, basic science to engineering, back to basic physics, I would say, and then with a glimpse to engineering. So one big challenge nowadays is the energy consumption of AI. And we heard already that gallium nitride is of course responsible for the revolution in light, but it is also responsible for now very feasible and energy efficient power electronics. So what is your opinion on maybe overcoming the energy consumption of AI by memristive gallium nitride?
Of course, gallium nitride already demonstrated its power. And first of all, I mentioned in lighting technologies, material number 1. I think that and it was considered the second, for many years, the second material of micro-nano electronics due to the possibility to use it in higher power, higher frequency electronics. And now, the gallium nitride penetrates into biomedicine. And this is due to the fact that it's biocompatible. And I have shown some examples. These liquid marbles, for instance, can play the role of bioreactors. And the interesting issue is that this shell is actually highly porous. That means through this shell, some gases freely can move. Concerning your question, I think that the material still has properties that are not, how to say, studied and realized. I can tell you about, we developed this kind of hollow tetrapods in close collaboration, and we see the interest. But on the other hand, until now, we have not used the interface between gallium nitride and zinc oxide. That means we realized that zinc oxide is stabilized at the interface. And we call this part induced chemical stability. But probably this interface can give some additional contribution to phenomena and to future applications. Because zinc oxide was considered very good. But the problem is not chemical stable. What we actually did, we demonstrated that at the interface it exhibits high stability.
Thank you. So it's about stability and instability. We learned also that there was a lot of instability in gallium nitride. Maybe this becomes now handy, all this research for memristive. So therefore, I think we can discuss this in the coffee break now as inspiration. So thank you very much for both speakers of this wonderful morning lecture.
Thank you.
2 minutes of the Republic of Moldova, my old friend Vyacheslav Saki. And we have today, in the second part of our morning session, welcomed speaker from the United States, honorary member of the Academy of Sciences of the Republic of Moldova, Professor Scopus. I like to give a few words before he starts, because he has really an impressive way, his scientific career and very special position in the modern science. Now he is an executive director for strategic research with the International Clean Water Institute at Virginia, United States. He received his PhD at the Virginia Polytechnic University and State University, and then had a postdoctoral fellowship at Kobe, again linked to Japan. But since then, he had a remarkable trace record. He was a professor at Virginia Technical and Marshall University, rector for research in South Carolina, executive director in New Jersey, etc., etc. I simply cannot tell you all his positions. And he joins two very rare abilities of a real generalist. His research is devoted to foresights, heuristics, artificial intelligence, and complexity science. And his main goal is to apply it for practical, very important social directions, like environmental science, protection of our environment, and in particular, I think, extremely important, environmental impact of micro and nanoplastics. Already this short extract from his curriculum gives us all reasons to look very much forward to his presentation today, which is called Leveraging Artificial Intelligence Information in Nanomaterial Synthesis and Device Design. Please have the floor.
Dear Professor Vasashta, I would like to ask you to finish your. I would like to ask you to finish your presentation in 25 minutes instead of 40, because at 12:30 the bus will be in front of the university to transfer us to the next destination, and we should be at 12:30 at the bus in the front of the university.
first of all, thank you for the kind introduction. And I can brief that introduction in perhaps 2 sentences. I'm a device physicist, and then I use the application of devices for multiple applications, including defense and security. So first of all, it's quite a bit of challenge to talk after a wonderful presentation. And the other challenge is to talk about something artificial for materials which we cannot see, which is nanomaterial. And the third challenge, which just got introduced by our chair, is to finish the presentation in 20 minutes or 25 minutes. So actually I planned it for 50, so I'm not sure I may have to either talk twice as fast or skip a whole bunch of slides. But I'm not sure if I can finish in 25 minutes or so, but I'll try my best. I'll try my best, but as mentioned, the presentation was for about 50 minutes or so, but I'll try my level best. But this is actually designed for students, because I think these are the things which I'm going to display. I think students can perhaps use for their research quite a bit, and as I foresee more and more application, you will be able to use that for multiple applications, as you will see. So, this is the only slide in my presentation which is generated by artificial intelligence. I asked AI to produce, I put the topic, I said, I want to give this presentation. Tell me how I can explain to people in one slide. Thanks to you, sir. In one slide, what my presentation is all about, how artificial intelligence can be used with nanotechnology. And this is what it generated for me. And I think it's mostly from cognitive sciences. As you could see, you see the brain and different types of sensing environment and conversion of that into an integrated circuit. But, you know, that's again artificial intelligence. So let me sort of take you through the presentation. Of course, I have to use my glasses. This is AI 101. Simply defining what artificial intelligence is, I guess all of you know, it's a simulation of human intelligence, such as learning, problem solving, decision making, and so forth. Machine learning is a subset of artificial intelligence, which is the ability to learn without actually programming, because it's sort of programmed already. Then deep learning is another subset, which is based on artificial neural network, which adapts from the vast amount of data. And then artificial neural network, which is an approach or to machine learning based on model as to how humans think or how the brain thinks. And then, of course, all of that depends on data. You have to have lots of data, and that's one of the challenges as far as the artificial intelligence is concerned. There are, on the left, I have put some general definition. Most of the tools which you use, such as ChatGPT, I'm sure all of you use that, that's agentic AI, because you have an agent. I don't use, of course I use agentic AI, but I use it as artist, and that's the reason I had coined this term called artisan AI. I use artificial intelligence to create something new. I don't use AI to create something for me, but create something new, and that's called artisan AI. We operate in a narrow artificial intelligence. The other two platforms, such as general intelligence and super artificial intelligence, they are yet to come. And as a group of lots of folks, as futurists, we have futurists in the group as well, we look into different aspects as to what future has to present it for us. So I'm going to take you through some of these definitions, because in fact we'll be talking about these platforms fairly frequently, such as machine learning. It enables computer to learn algorithmically from data. Then, of course, we have two types of platform. One is the supervised learning, the other is unsupervised learning. Deep learning, which is again a subset of machine learning that uses multi-layered artificial neural network. And then there are two platforms, such as the convolutional neural network, CNN, and graphic neural network, GNN, which we use as part of deep learning. Then we have reinforced learning, and then generative adversarial network. And generative or GANs, GN, it has two subsets. One is called generator, and the other is called discriminator. So it looks at the data, compares these two, and then it provides a computationally a product or a highly realistic output. Then we have variational autoencoders. That's a subtype of deep learning. These are probabilistic generative model and send data in latent space. Then we have natural language programming, such as ChatGPT. It's a text mining of information to discover trends, protocols, and knowledge. Bayesian optimization, this is based on probability. You put lots of parameters and calculate probability based on your problem which you may have at hand. Then of course, multi-fidelity modeling or transport learning and digital twins. These are surrogate models so that you develop something which looks similar to what you want to produce and then look at the outcome. So these are the terms which we are going to use in this presentation. This is simply, again, in the interest of time, I'm going to skip a few slides. This is to show about artificial general intelligence and superintelligence, which is not yet achieved, but nonetheless we are trying to put different platforms to make sure that we are prepared whenever the AGI or the artificial superintelligence comes into play. Eventual goal is to look something like this, or so that the data can think like our brain thinks. But the brain only uses 20 watts of power, so that's the response to Ryder's question, how we can get there, having artificial superintelligence, which uses less power. Again, I still have to mention, in the interest of time, DeepSeek, it was advertised roughly about 2-3 months ago, and the purpose was essentially the same. It was based on architecture, which only computes the problem at hand. Our computer, all the devices are active all the time, so it consumes a lot of power. If you change the architecture, such as an artificial superintelligence, that you only resolve the problem which is at hand, it would use less power and be more efficient. Half of the work, as mentioned, is for defense. So defense has lots and lots of application. Again, just to read a couple of them. One is for decision making, called OODA loop, observe, orient, decide, and act. Artificial intelligence is used for decision support. In defense, you always use contractors. So whenever there is a contractor, you want to see if that contractor would fit in the organization. Artificial intelligence is used to see if that person would actually fit into that environment or not. So there are lots of applications, but my purpose is to use for nanotechnology-based platform. What you see here are different platforms which are used for human augmentation, performance enhancement, longevity, and anti-aging. But of course, what you see in the center is what we plan to learn in this presentation. So here's the presentation outline. If I had a lot more time, I'll go through all of that in great detail. But we'll talk about materials genome, that is design of material synthesis, characterization, and then of course in device design. So that is the overall presentation of the outline. Here's a brief introduction. I think it's pretty much what I had informed, that overall scope ranges from atomic level synthesis to integrated system design. AI plays a pivotal role in accelerating material discovery, optimization of nanomaterials, and of course AI enables digitalization and automation of research work. So we'll see how we can do. I have done only small amount of work in artificial intelligence, in material synthesis and development, but nonetheless looking at different laboratories. there are different things which we can learn and of course use for our application. So again, as mentioned, we'll go through material design, synthesis, characterization, and application. And here are the motivation, which is accelerated discovery and design, complexity management, because we deal with lots of data, optimization of synthesis processes, integrated system engineering, handling of data overflow, cross-disciplinary synergy, sustainability and green chemistry, strategic technology advantage, and of course traditional method which we used in our laboratory, our trial and error, how we can change from trial and error to a little bit more systematic approach. So, Materials Genome Project, this was initiated by National Science Foundation a long time ago, and the idea was to discover, manufacture, and develop nanomaterials twice as fast and at a fraction of the cost. So this was then, they were using at that point statistical method. That is now transformed into artificial intelligence, and here's a case study of that called Chemical AI. Chemical AI was developed as part of the Materials Genome Project, and it was the first automated research platform for nanomaterial studies, enabling their synthesis, functionalization, and measurement of these characteristics. And again, just to read only a couple of that, it generates multiple synthetic pathways in minutes, computer-aided synthesis planning, plans chemistry synthesis project, and bring novel compounds forward in a fraction of time and cost. So that's essentially what the purpose, that you can reduce by trial and error, make materials more relevant and in less amount of time. So the first application of this material we used was for nanogenerators. These are energy harvesting material. So I'm going to first show the design of the material, and then I'll show also in the synthesis. But that's the work which I had done. But nonetheless, I wanted to study by what others have done. So if you look at energy harvester on the left, you can represent that in an equivalent circuit. And the energy of the harvester is written on the slide in terms of the material properties, in terms of its dimensions and so forth. So looking at the literature, piezoelectric constant, we would choose the piezoelectric constant which has the highest property if we could see, we could insert that in our material and make a highly energy nanogenerator or energy harvesting device. So this is the materials design. Not that you can actually make that because there are physical limitations. So first we used very similar to MATLAB optimization process where we would take data from the literature and try to insert that into a material to see how efficient devices we could make. And what you see is the PM and PT that has the highest, the piezoelectric constant. Not that we could introduce 100% in our material, but that's what this showed. So we tried to run several different optimization. And I'll come back to this experiment a little bit later. So first part was the Materials Genome Project. So I'm going to show some of the case studies after this slide. Again, one can use computational artificial intelligence machine learning to forecast material properties from structural information, which plays a significant role. There are several models which are used for regression, neural network, decision trees, etc. Some of them are physics-based, such as DFT, data-driven machine learning, deep learning, and hybrid approaches, such as physics-informed machine learning. We can calculate structure. There are different methods, such as random forest, support vector machine, deep neural network, convolutional neural network, and graph neural network, as I'll show you in the forthcoming slides. And then, of course, you can do prediction of their mechanical, electrical, optical characteristics, and of course there are metrics for it. So there are some of the case studies. Again, in the interest of time, I'm just going to read one or two. I can make this slide available to you if you like, because again, as I mentioned, there's lots of information and very limited time. One can do bandgap prediction using gradient boosting, random forest, and then of course in literature, people have achieved mean absolute error less than 0.4 EV. Polymer dielectric constant prediction using deep neural network, thermal conductivity in nanostructure using graph neural network, strength and hardness of alloys and optical properties of perovskites. This has all been used as part of case studies in literature. There are different publications which exist for these characteristics. Other case studies which exist are carbon nanomaterial classification, mixed nanocomposite using spherical nucleic acid. Yamakur et al., they conducted a different experiment and they created a database which was used to train a machine learning model which is capable of predicting activity of the spherical nucleic acid formulation, which enables systematic and independent optimization. Defect, that's very important, especially from device physicist standpoint. And of course, there are different platforms such as decision tree, logistic regression model, which are used to characterize defects, more specifically for metal organic framework. Inverse design is I don't want to call it a problem, this is a mindset where you look at the end result and design your material and synthesis processes based on what the end result should look like. So this is called inverse problem, and it's used in materials discovery, that given a target property, find the material. Nanomaterials allow that. So we have used materials by design for different types of application, such as photonic nanostructure, catalytic nanoparticles, energy storage, thermoelectric nanomaterials, DNA origami, mechanical materials, and plasmonic nanostructure for surface-enhanced Raman spectroscopy. In terms of material synthesis, I'll bring you back to the slide which I had before, but as a device synthesis person, we had used a method called Taguchi method. Taguchi method, if you have used in laboratory, this was essentially for people, those who used to work with integrated circuit. Because you have hundreds of parameters, actually thousands of parameters, how do you use minimum set of variation so that you have less trial and error and of course more reliable result? This is a method which is focused on variability reduction using orthogonal arrays, reduction of signal to noise ratio, cost effectiveness of experimentation, and factorial experimental structure. So AI-based approach now are evolutionary algorithm, AI augmentation design of experiments, and explainable AI. These are the methods which are currently used. So there are different laboratories. Some of the examples are given here, such as University of Toronto. They have self-driving laboratory for quantum dot synthesis. IBM uses RoboRxM for organic nanomaterials. AI-guided synthesis of metal organic framework at Northwestern University. Autonomous synthesis of perovskites, nanocrystal, and of course there's a consortium of laboratories making materials accelerator platform which integrates AI, robotics, and IoT, which is Internet of Things for closed-loop materials research to reduce obviously times for the discovery of the material. So as I mentioned, this is the case study which you see at the bottom. So in the first part, we tried to see, based on data which we produced, as to what composition would be by far the most efficient. And then we did that in for synthesis to see if actually we can design material based on that. And using again data and synthesis process, this is our ongoing research on energy harvesters. Deep learning, this was employed to identify optimal processing and material parameters that maximize piezoelectric coefficient. We calculated figure of merit, which demonstrates that composites which we had made outperform single-phase materials, primarily due to their ability to achieve composition that balance structure stability with enhanced electromechanical coupling, and of course that sort of advanced the research, and this research is still ongoing. So this is the work which we have done in our laboratory and continue to see what others have done and how we can tap into those types of platforms. But all of this data is not readily available, and that's one of the challenges. Part of the data is very expensive, as I'll show you some of the platforms which are commercially available and also some which are in open access. These are some of the case studies of the synthesis using machine learning, cell shape index, and nuclear area factors. People have tried to study nanotoxicity, which is critical for several different applications. In the third bullet, Chan et al., they proposed reproducible and high throughput synthesis methods for forming colloidal nanocrystals, which offer a systematic way to explore multidimensional parameter space. Lastly, in this slide, the quantum dots, because of the narrow size distribution, especially for optical characteristics, is very critical to use artificial intelligence, obviously, to make sure that you have monodispersity. And of course, artificial intelligence is used to enhance monodispersity by leveraging existing experimental data, and of course, more of that continues to, more and more data continues to be performed. In terms of materials categorization, there are different methods which are listed in here, and I'm showing all of you use in laboratory. But there is a rapid growth in nanomaterial demand, which requires fast and accurate categorization. AI can process lots and lots of data, so traditional imaging analysis being time consuming, we have to depend on AI, which enables high throughput automated interpretation of complex set of data. It enhances resolution, pattern recognition, and property inferences. So the methods which are used are supervised learning, unsupervised learning, deep learning, reinforcement learning, and generative models. And the goal again is AI accelerated discovery of structure-property relationship, as you can analyze large amount of data using cross-model learning between imaging and spectroscopy. So here are some of the case studies. Deep learning for transmission electron microscope image analysis. It gives us highly accurate data in terms of identifying grain boundaries and stacking form. Unsupervised learning for face segmentation. Artificial intelligence in atom-by-atom imaging. Generative model for data augmentation. You generate the data and then use the data to train your model. Spectroscopy, data interpretation, and the tools which are used are Google DeepMind, AI Digital Assistant Suite, and Atom AI. There are open source libraries such as PyTorch, TensorFlow, HyperSpy, LibraDEM, and of course integration of all of that with electron microscope, etc. obviously provides lots of platform for interpretation of data. And of course the output is listed on the right, such as active learning for intelligent sample targeting. This is a case study where you go from reverse design for materials genome to materials development, synthesis, and of course its categorization. In terms of device design, these are some of the commercial platforms, such as Materials Studio, the SALT system. It's very expensive, but nonetheless, laboratories such as IBM, they can afford it. So they have those types of platforms. Siemens has a system which is built for semiconductor and PCB design environment. ANIS, they have AI-powered simulation suite. And of course, Autodesk, which is your PDF maker. They have Fusion 360 with artificial intelligence. But as I mentioned, these are all commercial platforms. So here are some open source platforms which students can use, such as Vienna, AE, initial simulation. I'm sorry? Okay, I'll speak twice as fast. As I mentioned, sir, I have designed for about 50 minutes. I'm trying to do my best to finish in the time which I have allocated. And then quantum, espresso, LAMS, large-scale atomistic molecular massive panel simulator, and then there are cloud-based platform. Then, of course, there are some specialized artificial intelligence tools for nanomaterials, such as Matrogen, IBM AI-powered materials discovery, MATLAB, which I'm sure all of you use, Collimator AI, Sibali, etc. Again, you could search using artificial intelligence. Perhaps you may find some of these platforms. But I can make this slide available to you because it was designed with the intention to help students do faster research. AI-guided optimization of composite materials, such as machine learning, regression model, etc. One can create different types of data set for simulation and experimental results. Let me move on to other slide. There are 2 or 3 slides which I want to finish. AI-based immersive design of photonic crystal devices. The methods which are used are deep neural network for topology optimization and variational autoencoders. The impact being it enables scalable design of optical components for quantum photonic and on-chip communication. For biomedical application, where AI is used extensively, microfluidics devices are critical for lab-on-chip diagnostic, but their design space is most in non-linear. So obviously artificial intelligence is used. Methods which are used are reinforced learning, surrogate models, and Gaussian processes. Impact being it facilitates development of highly efficient portable diagnostic devices for use in point of care setting and resource limited environment. This is the course which I teach in University of Bucharest, how to teach students to use the Internet of Things software to learn and of course use artificial intelligence in their coursework. On the left, again, is a busy slide, but these are some of the platforms which we teach students how to use to maximize their research output. And of course, we also teach them how to make digital twins. These are replica of large-scale models to a smaller scale model, so that even before you design a thing, you know what the output should look like, and that helps them in the design of experiments. Augmented manufacturing platform, such as AI-controlled nanorobots, artificial intelligence optimized 3D nanoprinting, additive manufacturing, and quality control. AI is used for all of that. So here's the future of AI, advancing AI and machine learning, proliferation of autonomous systems, expanding biotechnology application, and of course, there is always risk of cybersecurity. So here are the key takeaways from this very quick presentation. And what you see on your right is the book which is coming out in about a couple of months, leveraging artificial intelligence and nanotechnology for materials design, devices, and manufacturing. AI transforms nanotech from discovery to system. Predictive, autonomous, and integrated workflow from lab to real-world systems. There are challenges such as data scarcity. You may have to create your own data. There's always a bias and there's always a noise. So we have to ignore that bias and noise to make real devices. Interpretability of model is also a challenge. The roadmap to adoption is you create data, create model, validation, and integration. And future trends are self-evolving material system, quantum AI hybrid approaches, and of course multi-scale modeling via artificial intelligence. But there are always ethical considerations, and those are listed in here. I specialize, as I mentioned, for defense application. We always look for new use technology. This is another book which should be out by the end of this month, and there we had discussed new use application of artificial intelligence. So if you look for this book, you will see that artificial intelligence not only creates new platform, but introduces data bias and scientific integrity. Human and ecological health, energy, which Reinhard has asked, the overuse of AI, over-dependence on artificial intelligence. That's the reason I had used the term artists of AI, not agentic. I don't want to be dependent on it, but I want to use as an artist. So these are some of the ethical considerations. I'll skip this slide, but nonetheless, I want to leave you with one term called Internet of Behavior. IoT with artificial intelligence gives you IoT. It provides lots of opportunity, but creates lots of challenges. So last, before you ask me a question, I'm going to ask you some questions. So here are those. What if AI could create materials beyond human intuition? What if AI created materials which refuse to be destroyed? What if an AI-created nanomaterial has characteristics far above those allowed by the fundamental science? And of course, it's trying to put human out of the loop. We cannot have human out of the loop. We have to have human in the loop to do research using nanomaterials. So with that, I close. Thank you.
Professor, for a wonderful lecture. Unfortunately, we have no time for questions now. During the coffee break, please ask any question. Now, very quickly, in front of the university, there is a bus which will transfer us to the destination.